All right. Thank you, to the organizers for allowing me to give this talk in addition to those lectures. And in fact, those of you who did attend the lectures may see some slides again, but I heard it was too fast anyway, so probably that should be okay. So yeah, so let me give a quick outlook. Whoops, sorry, I have some problems with this. Quick outline. So deconfined criticality. I think this audience doesn't really need an extensive introduction, but I'll anyway, just explain the kind of lattice phenomenon we are investigating, and very quickly about the field theory, which I'm, of course, not an expert on. So then I will turn to the kind of models that we have been using for many years to try to study this phenomenon of deconfined corner criticality. So these are what we call JQ models, and they can be used, among other things, to study, the potential deconfined critical point and related phenomena as well. But today I will focus on DQCP. So then, as everybody here knows, I think, a big question for DQC is, these lattice models we have, if they are really sitting at critical points, if we can really tune them to critical points, or whether they are, all basically first order transitions, sometimes maybe very weakly first order ones. So I will try to shed some light on this. And in particular, whether, if the model, in the end has a first order transition, if the exponents we extract still, make some kind of sense. So I will show evidence that that's actually the case. So then I will come to the issue of multicriticality, which is the main, new thing, I guess, about my talk. Some of this is published, but some of it is not published. So that's really, saying that maybe the deconfined criticality point has other relevant operators as well that need to be tuned. Okay, so the first part of the talk, the kind of models I will discuss, they would be of relevance when you talk about, DQCPs with potential emergent SO5 symmetry. I also want to discuss the case of O4. So we have a couple of models where we can investigate that. And that also gives some more insight into, what this multicriticality really may be. What is that multicritical point separating? So what we are proposing is basically that on the other side, so to speak, of the multicritical point, there could be a gapless spin liquid phase. And we have some evidence for that, that's really what happens. It's a bit speculative, maybe. Okay, so this workshop is called, bootstrapping nature, right? So I want to try to connect to nature a little bit as well by discussing some recent experiments that I think are sort of very promising for trying to see some of these things in a real material. Okay, so deconfined criticality, of course, the concept goes back to 2004, and Subir is here somewhere. Yeah, okay, good. But there were lots of works, preceding that as well. So let me quickly try to give you my understanding of this. So imagine we start from the 2D Heisenberg model, which has long-range antiferromagnetic order, and then we add some other interactions. And here the goal is to destroy that Nel order. So, the Nel state, of course, breaks O3 symmetry. And in this theory is basically a theory of how that antiferromagnet can turn into a dimerized phase or some kind of singlet pattern phase. It could also be plaquettes, as I will mention later. So you have some modulation of a singlet density, if you will. So that state breaks Z4 symmetry. You have 4 equivalent states, and the way they can fluctuate to each, among each other, at least on small lattices, correspond to Z4. So the surprising here, the thing here that was proposed was that this would be generically a continuous quantum phase transition instead of what you would expect in Landau theory. If you have two unrelated symmetries that are broken, you would expect a first order transition or maybe some other phase in between, some coexistence phase. Now, of course, even in the old scenario, you cannot exclude that if you tune two parameters in the model, that you could have some branch where you have this generic DQCP continuous transition, but then in somewhere else in the phase diagram, the transition could turn first order, and in between there would then be a multi-critical point. Now, this is not exactly the multi-critical scenario I will in the end propose, but anyway, even in the old scenario, we should expect some multi-critical point. Though generically, if you just take a model that has this transition, you would end up here or here. You would very unlikely end up at the multi-critical point. Okay, now the field theory, again, I'm not an expert, but let me give you some quick take on it. So if we just look at the antiferromagnet and its transition into a featureless paramagnetic state, then we can just use something like 5-4 theory or the nonlinear sigma model, something like that. But the VBS state cannot be captured just by that. But if we just look at this kind of theory, then we have in principle some topological defects in the path integral, and those are suppressed in the Nel state, and they proliferate in the paramagnet. So this kind of dimerized state, and this is what was worked out in those earlier papers that I cited before, Murthy and Sachdev and so on. They talked about how this kind of VBS state would correspond to the condensation of topological defects in a certain way. So then what was done? So here are these all the papers, was to introduce these spinor fields and write the magnetic order parameters as a bilinear of those, and then those would have to be coupled to a U1 gauge field, and then these hedgehog singularities would be monopoles in that description, and the square lattice VBS would correspond to condensation of quadrupled monopoles. Okay, again, I'm not an expert, but Subir is here, so if you have questions, yeah. Right. 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 But if you just take this one, you don't get the pattern, right? Right. Oh, yeah. No, I didn't want to say that it doesn't have the defects. It has the defects, but they don't condense in this way to give that, right? Right. Yeah. Right. Exactly. Well, thank you. Yeah. So again, I'm not an expert, but I hope I know what the theory talks about and how we can test it. So one thing here, with this VBS pattern, it breaks Z4, and that is, was conjectured to be similar to what you have in a clock model. If you just take a 3D XY model and add a clock perturbation, we know that that's dangerously irrelevant. So the universality class is still that of the XY model. So and there's some length scale associated with emergent U1 symmetry. So it was conjectured that this is similar, So that would mean that you can look at a theory which in fact doesn't even produce that one. It produces some U1 state instead. And again, I'm just flashing the picture, but this is one of the theories, the first one presented in the 2004 paper as the field theory describing the transition, right? But now, as you know, there's all these dualities, so there are many other alternative, field theories as well, and I will come back to that a little bit. But now, then, in terms of the calculations, what was, of course, it's very hard to study these theories. So what they did was large N calculations where they found a continuous transition. But the question, of course, then is, what happens as we go to, for example, SU2 spins. So that's where these numerical lattice calculations come in. So we have this class of JQ models that are, you can think of them as designer models for DQCP physics. And here I mentioned SU2. I will only talk about SU2, but I can mention, since in Shai's talk yesterday, he showed these comparisons between the theory as a function of n and numerical results as a function of n. So these JQ models can also be very easily extended to any n, and those results that were shown, those were from these JQ models extended to SUN. But today I will only talk about SU2. So if we think of the Heisenberg model, is the sum of singlet projectors, right? This is the singlet projector on two spins, and so the Heisenberg model has a minus sign for the singlet projector. So it somehow likes to have singlets on the bonds, but of course it cannot have singlets on all the bonds at the same time. But what we can do is we can introduce some interaction that likes to correlate those singlets that are projected by the Hamiltonian. So we can think of if this denotes a singlet projector on a bond, we can take products of 2, 3, or even more such projectors. And I think it's sort of self-evident, at least if you stack up enough of these, that kind of interaction will favor a columnar symmetry, columnar VBS pattern. And we sum them up, with the rotations and translations and everything. So the model itself doesn't break any symmetries of the square lattice. Okay, so the advantage of this kind of model, versus frustrated quantum spin models that people have been discussing for a long time, is that these are actually amenable to large-scale quantum Monte Carlo simulations. So we can actually study, very large lattices and so on. So the first version of the model that I studied was what we sometimes now call the JQ2 model, because it has these, singlet projectors, two of the singlet projectors in the Q terms. Okay, so it turns out that this model indeed does have, as you turn up this interaction Q, you do get a transition between these two kinds of states. Now, there are many versions of these JQ models. So it's really a whole family of models, and I will mention a few more. I mean, here you have, the Q3 interaction, Q2, and, Q1 is just, the J interaction. But the way you arrange these singlet projectors, in the product, that can also be varied and gives rise to, different kinds of states and so on. So this is like a machinery to test, quantum field theory predictions, but not only test, because sometimes we can also discover, things, that have not been, thought of before. So I would like to stress that this numerics is not just always testing; it's also like doing some experiments and potentially finding new fixed points even. So we can also make, with these kinds of models, we can also make direct contact with experiments. By the way, should I close the window here? There's a chainsaw going on outside, so I think I don't want to compete with the chainsaw right now. Okay, so so the last part of my talk, if I ever get there, will be about experiments actually. Okay, so let me quickly show you, what we can look at when we analyze the quantum phase transition in this model. So now we'll show some results for this JQ model. So we do simulations, no approximations, but we have finite size, of course. So everything has to be studied as a function of the system size, and we have to define our order parameters. So we have the staggered magnetization as the order parameter of the antiferromagnet. And then the VBS order parameter is really a vector. We have a dx order as I show here, but if I rotate this 90 degrees, then I have dy order. So we have two components here of a two-dimensional vector. And what we do numerically, this is sort of a standard thing in Monte Carlo simulations. You can define these ratios of different powers of the order parameters to get something dimensional. And then just by choosing factors, you can easily see what the value of this will be if you have an ordered state with that kind of order that you use the order parameter for, and what it will be if you don't have any such order. So these have the properties that one of them goes to 1 in the one that I call S here is for staggered magnetization. That's why it's S. Should go to 1 in the AFM phase and to 0 in the VBS phase. And for UD, it should be the opposite. So these are sort of state-of-the-art results in terms of system size and smallness of the error bar. So you see here, let's focus on this one first. This is the cumulant for the AFM order parameter. So you see here the system sizes are from 32 up to 512. And as you increase the system size, this develops into a step function. So in the AFM phase, which is here, it will eventually go to 1. And you see that it becomes very steep for the biggest sizes. And since the calculations are expensive, we don't bother to go further in there. So for the VBS case, it's the opposite. The step becomes 1 on this side and goes to 0 there. So what we then have to do is to analyze this kind of data as a function of system size and of course as a function of the parameter J over Q. Yeah.
The intersect at the point. So two plots. So all the 9 correspond to the different size of lattice. They intersect at a specific point.
Yeah, exactly.
Does that point have some special meaning, or it's just a...
Yeah. So that the good point. So we know that these values go to 0 or 1 in the phases, right? But at the critical point, if we have really a continuous phase transition, they should cross at a point. Well, even if it's first order, it should. So you see that roughly they cross at a point. So now, but not exactly. So now one can extract different types of crossing points, for 2 different system sizes, for example, or the crossing point. If you merge these 2 graphs, the ones that I had here before. So you can take, for a given system size, let's say this red here and the red here, and see where those cross. So based on those flows of those crossing points, you can extrapolate the critical point. I don't know, is that what you were referring to?
Yeah, thanks.
Okay, so I will say a few more things about that. So that basically shows, well, at least this is consistent with a simultaneous transition, meaning these transitions go to the same point. At first sight, this is also completely consistent with a continuous transition, because it turns out that at the first order transition, at least of some conventional type, there should be some negative peaks around the transition as well, which we don't see here. Okay, so let me discuss one of the important exponents, the correlation length exponent. And this is again the same kind of data from before. It's specifically from this paper, and now I plot both of these bin accumulants in the same graphs. So it turns out if you look at the slopes at the critical point, so we extracted the critical point, it's somewhere here, and now you see that the slopes of these increase with system size. So the higher the slope, the bigger the system size. And in fact, without giving you any details, I can just tell you that if you take the slope, meaning the derivative as a function of g, for two different system sizes, and here I use L and 2L, take the log of that, and that basically goes to 1 over nu. And what's 1 over nu? Well, you are more familiar with scaling dimensions, so this should be 3 minus delta, and delta should normally be the symmetric, what you would call the singlet, but here I didn't put any mark on it because it may actually, in the end, if we have SO5, maybe it's the one that in Lee's talk yesterday, I guess he called delta T, right? Because when you if you imagine that you have SO5 and you tune from O2, or let's say Z4, which has emergent U1 symmetry, so we can think of it as O2, going from O2 to O3 with SO5 in between. That should be something that explicitly, maybe or implicitly in the field theory would change the symmetry. So I don't want to put any indices there, but it's one of these scaling dimensions. Okay, so slope extracted as a function of L is shown here. Okay, then you can see that it definitely grows with L. Then we can take 2 points for L and 2L, for example, as I show here, and this is shown in the inset as a function of 1 over L. So for a given pair of system sizes, we get an estimate that I call 1 over nu star, and that should flow to the actual exponent here. And you see that it does. But this is where people sometimes are worried because they say, oh, the exponents are drifting, so that's strange. Well, this exponent extracted in this way is drifting, but that in itself is nothing sort of alarming or unusual. Exponents always drift because there are finite size corrections that are not included here. This is just the behavior for very large size. So maybe what's unusual here is that the drift is pretty large. So here the system sizes are already around 100, and here the biggest size is almost 500, and still you see that there's a pretty large drift, and it's not super easy to get a good extrapolation. But one nice thing is that the results for the dimer, and here I call it Z, the Z component of the AFM order is what's used. They at least seem to have the same behavior. But now we can do something else. We can also, directly, try to get to this scaling dimension. So this is, for some reason, not often done for this scaling dimension. Of course, when people look at the order parameter, we'll always look at, correlations as a function of distance, and that, decay gives us, 2 times the scaling dimension. But here we can also do that for what's like an energy correlation, but it's just part of the energy. It's the Q term, but Q is what drives the transition, right? So then the QQ correlations should actually give the same exponent. It should give that delta. Now there's a little bit of a complication here, which I don't want to go into, but this is what I say here, that it's the uniform part. Let me not talk about that. It's sort of a distraction. But anyway, so what we have in the end is a correlation function that decays as a function of distance. And now I do it in 2 different ways. One is in a big system, L is 256 as a function of X. Okay, that's the red set of curves points. And then we can also look at the longest distance of the finite system and plot it as a function of system size. So X is L over 2 minus 1, it turns out. So it turns out that the uniform part you can access at odd distances. Let me not get further into that. But here you see you have a very nice power law. Not much drift in some sense, right? It's really a very nice power law. And if you extract, that delta from there, you get the line here. So, they agree, not perfectly, but, the statistical error. So the size of the dot there is roughly the statistical error. And the line here is a double line, but it looks like a single line. So within 2 error bars, these estimates agree with each other. So I think that's pretty nice.
Anders,
Yeah.
so what controlled the correction to the ratio of U1, of the Binder derivative?
So that should be what we in condensed matter theory
Is the
call
omega?
the exponent omega. You would call it the first irrelevant operator.
Okay, so if
but
that's not too irrelevant, it will give you a big correction.
Well, see, the thing it's not just about how relevant or irrelevant the operator is, but how much it appears in your model, right? If you have irrelevant operators, you don't control well. Martin Hassenbusch controls, how much irrelevant operators he has in his models, but here we cannot do that. I guess we will hear about that later today. But we are just given some strength of the irrelevant operators in our lattice model, and if they are very weakly there, then we don't see a big amplitude. You would see the same power law, for the correction, but with a smaller amplitude, right?
But that's specific property, right? If you change lattice model and you still see the drift.
Yeah, you should still see it, but maybe the amplitude of overall magnitude of the correction would change. Actually, it may not be an irrelevant operator. In this multi-critical scenario, maybe it's actually the second relevant operator that causes it. It's not so easy to say, but it's sort of even consistent with that. But whatever it is, it's something that should not be, it's not crazy or anything like that, as far as I can tell. So, yeah.
Okay, size omega, you should have some estimation, right?
Yeah. So this power you see here is less than 1. So I forget what it is, but it's like 0.7 or 0.6 or something like that.
Okay, so it's still very irrelevant. So
Yeah, exactly. I mean, you can sort of by eye see. If it would be a straight line, it would be 1, right?
I see.
Yeah.
Thank you.
Okay, so now the final extrapolated value. I should say that it also agrees with what other people have done. Well, sort of, because nobody has really done it super careful except Adam Nahum and John Chalker and collaborators. They looked at a 3D loop model, which actually is very similar to the JQ model, because when we simulate the JQ model, we actually simulate a loop model. But they took that sort of loop model and made it space-time isotropic. So it's really a cube. In our case, it's maybe what do you call it? An elongated cube. Forget what that's called, rhomboid or something. But that shouldn't really matter. But they get, very close to the same value. They say, okay, there's some drift, but for the largest sizes, it seems to go like that. But our error bar is probably the smallest, I think. So, what this shows is that, maybe in the end, this model has a weak first order transition. And in fact, in the next slide, I will almost argue for that. But at least, when we get good agreement like that, it seems like we must be very close to some critical point. But one problem, of course, as I think people know here, is that we violate, for this particular exponent, we violate this bound, which, if I understand correctly, is a very sort of general bound. If you have one relevant scalar in a CFT, this has to be the case. This is not really compatible with that. But this talk is in some sense about, showing that maybe we actually don't violate the bound if we have more relevant scalars. Well, I mean, if you have more relevant scalars, we may not violate any bounds. Let me quickly say about emergent U1 symmetry. So this is one of the first things that was done with these JQ models 15 years ago now. So I already introduced the order parameter here. Now let's make a in the simulation, we can look at the individual configurations and we can compute dx and dy, and we can make a histogram. And this is, for not very big system, but it takes a lot of effort to make these histograms smooth. But this is sort of slightly away from the transition, but pretty close. The transition drifts as a function of system size as well. You can think of it as close to the transition. If I change a little bit, it's actually a little bit inside the VBS phase, because if we actually go in the VBS phase, we see like a ring with no weight in the middle. Here it's so close that there's some weight in the middle, and then it just becomes a very smooth bump there with no feature of Z4 symmetry breaking, which we do see if we go to bigger lattices deep inside the VBS phase and so on. But let me not talk about that, because it takes too much time. But so this we saw this U1 symmetry a long time ago, and then of course, as you know, Nahum et al. Within their loop model thing, they saw also SO5. They looked at such correlations between the magnetic and VBS order parameter. So you can think of SO5 as this emergent U1 combining with the O3 of the antiferromagnet. Now, one thing I want to go to now is to ask, well, what happens in this JQ model if you take Q terms with many singlet projectors? Like, yeah, please.
Why do you say O3 instead of SO3?
Well, maybe I should say SO3. Yeah,
because I would think of it as SU2, so you wouldn't have this extra Z2.
Right. Yeah. No, it will. I'm a bit sloppy with this group theory and symmetries, and I think we cannot detect the difference in what we are doing. So yeah, I think it should be SO3, because you just have the
Sure, but where do you get the extra Z2?
Right.
So you're saying it should?
It should be O3. Okay. Anyway, maybe we can discuss that after. I know, I just know that I cannot in these kind of histograms see the difference, but it may be SO3. So your exponent seems to have taken let's see now. No, I don't think it, because this is 2 + 1D. So the Harris criterion is 2 over. Let's see. D times. Yeah. That's a good point. I haven't thought about that before. But we have many examples with the Harris criterion. I think is actually seems to be something that's not always valid. So we can discuss that after. But I wouldn't be too worried. Even. Right, but I think the Harris criterion is in principle something that should always apply, right? No, only for random. Okay. Anyway, let me ask what happens for, when we extend these Q terms. So the JQ2 has sort of the minimal number of singlet projectors, and now we can go to some extreme case, make these, very long, and very large, and say, well, then it looks like we should get some nucleation. These terms should nucleate some, regions of VBS, and maybe we just get the first order transition. So we looked at in this paper, which, the main topic of was something else, but we looked at, this kind of JQ6 model where the Q term, projects that many singlets. And now this is a series of histograms which are doing the same as here, going very close to the transition, and seeing that here you had emergent U1. Here you don't see that. So in the AFM state, but very close to the transition, you see that you have a blob in the middle, and you have some sort of 4 satellites there as well. If you go very deep in the AFM phase, you just have a blob in the middle. Now you go to the opposite side, well, then you see 4 blobs, and that's because you are in the VBS states. So then you have 4 different, patterns and the Z4 symmetry breaking eventually in a big system. But then as you go between, you see that you have actually coexistence. Here you see the 4 VBS blobs and the AFM blob in the middle. So this is clearly a strongly first order transition. And by looking at the order parameters and so on, we see that there's coexisting large order parameters at the transition. So so then, this was JQ6 and this was JQ2. So then it seems, well, if you go to n equals 2, 3, 4, 5, and so on, at some point, it should change from continuous maybe to first order. So let's look at that. And this is actually some unpublished results that I'm going to show you now. So we're going to look at the spin correlations and the dimer correlations at the longest distance of the lattice. The L over 2, we could also look at along the diagonal, but I think we look at L divided by 2 here. So this is for the JQ4 model, and these are spin correlations at the longest distance, or at distance L divided by 2, and I plot it as a function of 2 over L. And these are for 3 different Q values very close to the transition. So you see in one case it starts to go to a finite value, here it dips down, and here it also dips down a little bit. So the transition should be somewhere in this bunch, right? And now let's look at the dimer correlations, and they are color coded in the same way. So here you see where the AFM order went to a finite non-zero value, this starts to really dive down and so on. So, okay, but then you see, well, wherever the transition is, it's not completely clear, but it looks like eventually it will do something like that. So these order parameters will extrapolate into small but non-zero values. So that means you have coexisting order parameters at the transition and long range order. So that means first order transition. Now let's go to the JQ3 model. Here I only have one set of curves, and for as far as we can tell, super close to the transition point. And here I have just drawn some lines. In principle, it can be some. If we have a critical point, of course, there should be some. The exponent should not be exactly 1, but this is just for guide to the eye, so to speak. But here you see that the spin, correlations start to go a little bit up here. But the dimer correlation also starts to go a little bit up. So that means that they both seem to be coexisting at this point. So again, that would mean a first order transition, but here, super weakly first order transition. You see the values that these would extrapolate to would be like 10% of what it's in that case. Now let's go to JQ2. So this is again also close to the transition, but things are very sensitive, as you see here. So here I think we are actually not quite, we didn't have quite the correct critical point. So we have another set of calculations running. I didn't plot it yet, but you see here it looks like the dimer correlation goes to 0, or it may actually start to dip down a little bit. And the spin correlation starts to go up a little bit. So this seems to have a weak AFM order, but maybe no dimer order. So this may not be exactly at the critical point. But now you can see if you only had data, let's say up to here, which is already maybe 100 by 100, it will look continuous. But when you come to really big sizes, it starts to look like, most likely, I would say this also will show first order behavior when we do it more carefully. But it's not even completely clear. But I would say if I were a betting man, I would bet that it's very weakly first order. Okay, so hopefully we will have some paper at some point about this. But now you can ask before I showed you how we extracted this scaling dimension delta, and that looked very nice. But if the transition eventually is weakly first order, do those numbers even make any sense? So now what we can do, so make any sense would be be, well, do they reflect some critical exponents of some nearby critical point, which we would hope, of course. So now both the JQ2 and JQ3 models, as you saw, look like they're maybe weakly first order. And presumably they are close to the same DQCP. So then we can check if we get the same exponents or not. And now I will look at the same thing as I did before, this QQ correlation function, which gives us this scaling dimension that I talked about before. So now I will plot it in a slightly different way. I will take my correlation function and I will multiply it by what is the best power of the distance, so that it should go to a constant. Sorry, I'm really not very good with this microphone. Yeah, so that will be a nice way to plot it. And again, this 2 delta from before, it should be around 1.6. Now, what I will actually show is a completely different set of calculations for some reason that I don't want to get into. But the previous set of calculations were actually at finite temperature, where the inverse temperature is proportional to the system size. So that would be okay when you do a critical point with dynamic exponent 1, which we expect. Now we can also do a projector QMC where we really go to 0 temperature in a slightly different way that I mentioned during my lectures. But it doesn't really matter, but just for to be full disclosure, it's a different set of calculations, which is good because now we can confirm that we actually get the same exponent as before. Now the best exponent for 2 deltas is to be 1.59, which is also compatible with the previous one. But here you see, again, this is as a function of half the system size, and you see initially there are some corrections, but then this becomes very flat here, and then the error bars, unfortunately become big. But you see it's very flat. Okay, so how about the JQ3 model? And by the way, this is again, a scaling correction, which seems to, decay very quickly in this correlator. In the JQ3 model, we use the same exponent, 1.59. And then you can see we again have some correction. In this case, it approaches, this line from above. Here it was from below. But it does show this range, although it's not a long range of points, maybe from size 25 or L/2 from 25 to 50 or 55 or something. And then it starts to take off very clearly. So my interpretation of this is that, well, this shows a critical behavior up to the biggest size I did here, but the error bar is big, so who knows what actually it's doing, but the error bar within error bars it's consistent. But this one does flow to the same power law behavior before it runs away from the critical point. So this seems to indicate that whatever makes the transitions first order is more strongly present in the JQ3 model, okay, than in the JQ2 model. But it does seem like the exponents make sense, because even if this one runs away, there's a range here where we analyze the data and it looks like the same power law. And if you use other powers here, it looks less nice. So this is like the optimal exponents also for this one. So this is evidence that what we extract is actually something that reflects an actual critical point. Yes, please.
So interaction. So for example, if the n is very big, like a Q6, will the interaction be uniform or not?
So if I look at the Q6, I will not see anything like what I just showed you. Sorry. So for Q6, we see nothing like this. And to be honest, with Q4 we didn't try, but I think since Q3 already only has a small range, and Q4 was very clearly first order. I think JQ2 and JQ3, those are the models where we can see this, and of course JQ2 is better than JQ3. Right.
So the question, like for the Q6 case, will the Q6 coupling have any effect on the IR phase at all or not? Because if it's uniform, it seems it won't affect your deep IR behavior. Is that true or?
Also, you mean, does the Q6 model have anything to do with DQCP at all, or what?
No, I mean, the question is that, so the coupling Q6 has any, will it have any effect to the IR phase? I mean, is that,
Okay, maybe you are asking something that we are actually doing, but which I'm not going to really talk about. But, you know, we can, let's say we put Q2 here, let's say J is 1. And then we put Q6 here. So if Q6 is 0, we have a transition here, you know, VBS. And with Q6, you know, we get a strongly first order, you know, but also VBS here. It turns out that, well, you know, there's a phase diagram like that. So, you know, the Q6 term or other terms that we can add, you know, eventually takes this almost continuous critical point and makes it very strongly first order. So we can actually look at the scaling as we go on this coexistence line, and that gives us also critical exponents. But that's so much preliminary and in progress that I don't want to talk about it, but I will talk about some related things. And, you know, so it may be that maybe the critical point is the actual critical point is a little bit on the negative side. I don't know if this was your question.
yeah, that's one whole question I want to ask. So if you take both like a Q2, Q4 couplings together, and then you can get some different.
Yeah,
phase.
yeah, exactly. So yeah, so I will get more to this in a well, soon, hopefully.
And one more question. So why do you expect that also the Q2 and the Q4 interactions will give you the same DQCP?
Well, you know, Occam's razor, like, okay, that would be the simplest. The simplest explanation would be that these all contain some other, you know, field theory operator that is relevant. And, you know, the more I stack up these singlet projectors, the more. But, you know, that's just my conjecture. I cannot prove it.
If
Yeah, we don't break any symmetries, right? Yeah.
yeah, but I mean, like in like the 2.2 dimension, we could have both like a 3D model or three critical as a model or something like that.
I mean, it's possible, but let's not discuss that because, you know, we can speculate about that forever. So in our scenario, you know, there's something that's growing, you know, some relevant operator that grows. But, you know, you can prove us wrong maybe later, who knows?
Okay, thanks.
So let me tell you about some other signatures of DQCP very quickly that may be of interest to people here. So this is a collaboration with Soyoung Meng and his students when I was at IOP in Beijing. And we collaborated with, you know, field theory friends that, as you see here, you probably know them. So in this case, we looked at a slightly different kind of JQ model, which should have a O4 symmetry if it has a continuous transition. So we call it the planar JQ model. It's really the same, but we perturb the J term in this way to make it O2 ordered instead of O3. That's not so important here, but that just happened to be the model. And then we want to look at the dynamic spin structure factor, which, for example, you can measure in neutron scattering experiments if there's some material that would have these features. So then we have to do what's called analytic continuation, which is a way to go from imaginary time correlations to real frequency spectral functions. And, you know, this is some cut through the Brillouin zone and just showing, you know, that spectral function in some color coding. So, you know, brighter colors means more spectral weight. Okay, so then, you know, our field theory friends, they were quite excited about this, especially when we told them that, oh, this lower bound here has a very simple form. You know, we just had our results, and then the student Nysen, we asked her to play around with different, you know, sines and cosines, and she found a form that fit really well. Let me show that form first. So it's that form that describes the lower bound with just some overall factor. And then our field theory friends immediately said, oh, that's the dispersion relation for the pi flux model. which you can think of as a mean field model of this version of among all these dual field theories in the web of dualities. We can look at the NF equals 4 compact QED3. And of course, there are many other ones, but the point here was that if you can only do mean field theory of these models, because they're very complicated, mean field theories or some perturbation theory for interactions, which out of all these field theories has the best starting point at the mean field level. And then it seems like this one has, because, well, again, I'm not the expert here, but apparently this pi flux state is like the starting point or the mean field version of, yeah. Oh, okay. So, this is then, the theoretical scenario based on the pi flux state, where the spin, which we need for the spectral function is expressed with the fermions in this way. Now, I should say that this already takes into account interactions at the RPA level, but even just at the mean field level without any interactions, it looks already pretty good, but it becomes even better at the RPA level. So you see that it actually works quite well. So, these spectral functions are very broad, for given momentum, there's a broad range in energy, and of course that reflects spin on deconfinement, that you really have these two partons that we call spin-ons in the quantum magnet that are essentially two independent particles. So one point of this was that actually this model that we studied, we also know now is weakly first order, quite clearly. The transition is. This is done at the transition point, and it still looks, very good. So the weak first order transition should mainly be reflected in the fact that, there should be a tiny gap at this pi 0 point here. Okay, so it looks like I probably don't have time to talk about everything I wanted, but I guess we had lots of questions. So I can probably go over just a little bit. Probably solve the time. It would also be better. So now let me talk about the second relevant operator that we have identified in this paper. With the Q2 term is that we are using the JQ2 model is this one. So let's not get into why, but at some point we decided to calculate the scaling dimension of this kind of operator. And again, we imagine now that we add it to the Hamiltonian, we take the critical JQ2 model, and we add these Z terms, with all rotations, translations, and so on, with some, strength Z. So, there's no change in symmetry here. The lattice model, the new lattice model that we get doesn't break any additional symmetries. And then we can just say, okay, we don't actually put it in, but we compute its scaling dimension. We sit at the critical point. And this is shown here. Now, this is a little bit complicated in the sense that these single operators, they do break some, rotational and reflection symmetries, right? So to avoid problems related to that, we pack that operator into a 2x2 plaquette to avoid any sort of picking up any other, symmetry breaking operator, the scaling dimension of. Okay, so then again, we fit some lines to correlation, well, some power laws to correlation functions. In a couple of cases here, we don't add any corrections, and then in one case we add a correction also, but they're all consistent with the scaling dimension being 1.4, which is very different from 0.8 that I showed before. So this is where maybe we can get out of the bootstrap bound. Yeah. No. I'm saying that there are two of them. Okay, so I guess maybe you are mystified by the fact that why we don't pick up any of this 0.8 in this thing, right? because right, yeah, so unfortunately I cannot answer that question or comment on it, but I can just say that it looks like we have two relevant operators that at least don't break any symmetries of the square lattice and the spin rotation symmetry and so on. So whatever it means. Yeah, let's talk about it after, because I think there's lots of interesting discussions to have what this means. I can maybe only tell you that it seems like we have a different scaling dimension for that and that, but of course the lattice operators would in principle contain an infinite number of continuum field operators. So then it's a little bit surprising that when we just compute the correlation of this one, that it doesn't have any content of whatever operator gave that scaling dimension, right? But the Q term, as I have discussed, maybe with the JQ model itself, we are not exactly at the critical point. So there's something already there that perturbs it. So maybe that operator is actually, the one that we are measuring to be scaling dimension 1.4. Maybe that's a little bit contained in the Q term as well, and that's what causes the transition to be first order. Now, there's actually a very interesting theory scenario by Yichong Yo, Zhenke Xu, and Da-Chuan Lu, Yichong's student, where they actually analyze this interaction, and they propose that it corresponds to actually a current operator in the field theory that in principle could be in the field theory. And they also comment on the fact that it's actually possible that this is included at a very weak level in that operator. Right. Well, that's what I don't know, right? I mean, we don't break any more symmetries, but we seem to have, I mean, concretely what I'm telling you is that if I compute the correlation function of that operator, it has decays with an exponent giving me that scaling dimension. If I do it with that operator, I get a different exponent. So that must be in that their, field theory operator contents are different, right? Yeah, exactly. The weights are different. Yeah. So the weight of the 1.41 in the Q operator seems to be super small. But as I increase n, the weight increases. That's the picture we have in our mind. Yeah, so that's what I mentioned here. Yeah. Yes. Okay. So you need Z to contain very little of Q because we don't see any of it here, right? And then for the transition to be sort of almost tuned to the multi-critical point, I also need the content of Z in Q to be low. That's exactly right. Yeah. So exactly why that is possible, I cannot say, but there's at least some suggestions in this paper. And I do think that this numerics should be taken seriously. Otherwise, I think I would not tell you about it. But let's see. So now I guess 1 hour is gone, but there was a lot of questions. So can I take 10 more minutes at least, or is that okay? Okay, I mean, everybody else has taken at least 10. So, okay, let me try to quickly see what should I tell you about then. Should I tell you about these models? Okay, so there's something called the Shastri-Sutherland model. Second. All right. Okay, so there's a model, like that, which is of relevance to some experiments. Let me not talk about it, but Subir has studied it with his collaborators and argued that it also has a DQCP, although the kind of plaquette state you have there is only a twofold degenerate, but it can combine with the O3 antiferromagnetism and give you O4. So what we studied again as a designer model is what we call the JQ4 model, checkerboard JQ model, where we put these Q terms only on every second plaquette like that. So that allows you to have a twofold degenerate plaquette singlet solid. And we basically, to make the story short, we see that we have coexisting orders at the transition point. So we have consisting, plaquette singlet order and antiferromagnetism. So it looks like pretty strongly first order transition. But that's not the end of the story, because we actually can show that we have emergent O4 symmetry. And this is, one illustration of that. This histogram has one component of the magnetic orders in one axis and the plaquette order in another one. And when we go through the transition, we see a point where, again, we look at these histograms and we can see O4 symmetry. Okay. And these radial fluctuations are due to finite system size. Now, very recently in this paper, which is actually about the experiments, but one of the referees asked us to provide some more evidence of, well, in that paper we talk about O3, but we also looked at this O4 with a cross correlation ratio, so an expectation value of the product of both order parameters. Now, if we have O4 symmetry, you can easily compute that the value should be 2/3 if the order parameter sits on the surface of an O4 sphere. And as a function of Q, indeed, you come very close to that value. So we believe that it has O4 symmetry, but it's a first order transition. So, that's sort of not what people would expect. So the interpretation of that is that, well, we actually sit close to a deconfined critical point, which has O4 symmetry, and that O4 symmetry can survive for some time. I can even use this as illustration as we go into, a coexistence line like that. In a similar way that we can have emergent U1 symmetry of the VBS, even inside the VBS phase, that this symmetry can survive. So that's the the idea. And then, okay, what I will skip is that in the Shastri-Sutherland model itself, which was sort of the motivation initially to do the checkerboard JQ model, we believe that we have a tiny spin liquid phase. Okay, so that's important for what I want to. And sorry, I don't have time to talk about that, but I did mention it in my lectures, and you can look at the papers. But now, so now I guess this will be sort of my concluding slide. So the generic DQCP scenario was that, okay, if we just take some generic model with one parameter, we tune to a transition point, that should already be generically the DQCP. But as I already mentioned, it doesn't exclude that there are also first order transitions somewhere else in some extended phase diagram. And of course, there's been a lot of discussion, including here, if these continuous transitions can even be reached at all. Maybe they don't exist in the parameter space in the real world, so to speak, but you have to go to non-unitary CFTs to really come to those points. And one reason for proposing that was that it seemed like many different models were sort of very weakly first orders. It looked like, okay, generically you always end up somewhere here, but never here. So that must mean that this is somehow inaccessible. Okay, but I would say that, well, now we have shown that you can tune from strong to weak first order, and maybe that point is accessible in some case where you can really tune away that second field. But now from the work on the Shastri-Sutherland model and also work on other frustrated models, we know that sometimes there are spin liquids between the antiferromagnetic phase and these dimerized or plaquette phases. And then we can combine models. We can combine the JQ model with these frustrated spin models and argue that the phase diagram, the unified global phase diagram, actually looks like that. This transition line, at least for SU2 spins, may actually not just be a line, but it may open up to a gapless spin liquid phase. And this is also what this PRB paper by Yo and Zheng Xu and their student Lu, what they proposed. Well, what they commented after we showed them this result, they revisited their theory and said, yeah, that line can actually become unstable to a spin liquid formation. So this is the multi-critical scenario that we propose. We are still investigating it, so maybe it's a little bit speculative, but I think it's actually at least worth examining. So maybe I don't have time to say anything about the experiments, but let me just say that now there is actually this experiment, this material, which is strontium copper borate, which people have studied for a long time, but only recently under very high pressure, and even more recently under high pressure and high magnetic field. And it has some low temperature plaquette singlet phase and antiferromagnetic phase. Intriguingly, in between, nobody has seen any phase transition, and that would fit with this spin liquid that we have proposed. But there are some experimental limitations there. Now, the really exciting thing is in this paper here, which is actually, I guess today, even the next version will appear online. We just posted a new version, where at high pressure here, 2.1 gigapascal, and for the theorists and even people like me before I got involved with this, that doesn't tell me anything. So it's around 20,000 atmospheres. That's what 2.1 gigapascal is. You see that the plaquette singlet order as a function of the magnetic field really is suppressed to almost zero, and then antiferromagnetic order sets in. So that looks very similar to DQCP. The experimentalists do that at up to 2.4 gigapascal, and it looks quite similar, always very low temperature, which is actually surprising because just quickly show here without really telling you much, but the transitions are actually first order quite clearly. So then you wouldn't expect to have very low TC unless you have an emergent ON symmetry, because in 2 dimensions, and this material is very 2-dimensional, you cannot really break the ON symmetry at finite temperature. So emergent symmetry can suppress the order, and furthermore, some scaling in the temperature is seen, and it sounds a bit too crazy, but the exponent is even very close to the DQCP estimate. So the sort of putting together the experiments and what we believe from theory, we have some kind of phase diagram there, but I'm out of time, so I'm not going to discuss it, but I would be happy to discuss with people after who are interested. Well, thank you very much.
There's a question on
Oh, Frederick.
Yes.
Hello, Frederick.
Hi. Can I say something? Do you hear me?
Yes.
Yeah, I can hear you.
Okay. Hi, Sand. I understand. I have a question about the first part of your talk, actually. When you said that in the JQ6 model, you have a very strong first order transition.
Yeah.
Did you check the finite temperature? Because this first order transition should terminate at a critical point somewhere.
So I didn't quite get the last sentence. You said that means that it's not close to a critical point because
No.
it's strongly first order?
No, I was asking about the properties at finite temperature.
Oh,
Whether-
finite temperature.
Because the first order transition should
Yeah.
terminate at the critical point, and since you're doing quantum Monte Carlo at finite temperature, I was wondering whether you actually observed or
Yeah,
looked
yeah.
for such a
So you know,
critical point.
in that JQ6 columnar model, we have not looked at the finite temperature phase diagram, but in that same paper, which is a very long paper, we also study a plaquette state. You know, a model which has a transition from an antiferromagnet to a plaquette, you know, fourfold degenerate plaquette state. And there we looked at the finite temperature phase diagram, and it's quite interesting. But I guess you know, I cannot go into it now. But if you look at that paper, you will see some finite T stuff. But yeah, it would be interesting. I guess maybe you are asking because you are thinking about these icing water liquid like critical points at finite T. Maybe we could have something like that.
Yes, I think so. I think you should. I mean, the first order transition in 2D should continue, is expected generically to continue and terminate at the critical
Right,
point.
yeah, no, that's a good point. I think we should definitely look at that. Thanks.
You're welcome.
Yes.
Just a comment about.
Oops, no, no. Uh-huh.
What?
Yeah, I know, yeah. Right. So maybe I can make another point here about this phase diagram too. One thing which we cannot exclude, and there's some tantalizing hints, but I don't want to say in detail, but you know, it could be that there's also a coexistence state here, that this actually splits into two lines. We actually don't see that, but when we compute exponents along this line, it's like we see two of these new exponents, one for the AFM and one for the VBS, which I don't know if that's possible if we only have one line that somehow in the Hilbert space, these, when the symmetry is broken, they just separate and there's still just one line, but yeah. But then, Subir, what do you think if you have those transitions and you approach, you know, I don't think you discussed the tip of the spin liquid. So maybe there's some, you know, emergent SO5 or O4, whatever, as you approach the point and. I see. Oh, so you say that even the multi-critical point in your theory is not Lorentz invariant. Yeah. But in our case, it seems to be. So then maybe your theory does not explain that point. Well, I mean, at least the dynamic exponent seems to be one, right? Right. Well, of course, maybe I should be careful with that too, because we have all these anomalous scaling behaviors, and some of them seem to also show deviations from z=1. But
Before we get to very fancy conformal arguments, it would be good to really test even simple things. Like
yeah, exactly. There's another question.
Last question, perhaps.
Okay, so in tubular QDC case, the story is that if there's no fixed point, then there will be spontaneous mass generation for the fermions. The phase will be gapped. There could be small mass gap. Case. So near the phase transition, is it possible that for you to estimate the possible mass gap?
Yeah, well, of course, you know, there's some limit to our precision. So, you know, we have computed, you know, the singlet, triplet gap and things like that. And, you know, it seems to scale to 0. But if it's something super small, you know, like, for example, this first order transition in the JQ2 model, if it's first order, it's extremely weakly first order. So that also would mean that the gap is super small and it's hard to compute.
But at least you can give bound about the possible
Yeah,
mass
in
gap.
principle, we should be able to give some upper bound, but we haven't tried that. But yeah, in principle, but since it all depends on some extrapolation, in the end, then you have to propose a form for, how does that mass gap affect the size dependence or something like that? Because, if you don't have a specific form, the extrapolations will be very sort of uncertain.
Yeah, thanks.
All right.